Hey guys, so let's start the seventh Boolean law, which is distributive law. Okay, so within distributive we have like three types. The first one is x multiplied with y plus z is equal to xy plus xz. Now you have come across this in mathematics as well. Okay, now in the previous video you learned about principle of duality, so in which I told you that from one Boolean expression you can derive another one. So when you'll apply Boolean expression to this first one over here, you'll get this second distributive law, but this is only applicable in computer science, okay, not in mathematics. So the second distributive law is x plus y into z is equal to x plus y multiplied with x plus z. Now there's another distributive law which is called the third distributive law, and it's like completely different, not related to anything, something completely new. Okay, so which states that x plus x complement y is equal to x plus y. So let's first draw the logic gate representation for these. So the first distributive law states that x multiplied with y plus z is equal to xy. If you want, you can put that in bracket as well, plus x into z. Okay, so this is the left hand side and this is the right hand side of the expression. So let's draw the logic gate representation for this LHS. Now y plus z, plus means or, so we have y z and you are passing them through OR gate, so you'll get y plus z. Now we have x, and which is being multiplied with y plus z, so you take one x as well. Now this y plus z and x are passed through or are given as input to AND gate, so you'll get x multiplied with y plus z, which is similar to, let's draw the gate representation for this RHS. You have xy and you're passing or giving passing them through AND gate, so you'll get x multiplied with y. Now similarly you have x and multiplied with z. If you want, you can take one x from over here and then write z. So just let me show you what you can do. If you want, you can take one x from here and then one z as well, and you can again pass them through AND gate. Okay, but my advice to you would be that again take another x and z, pass them through AND gate, so the output from this AND gate would be x multiplied with z. Now you can give these two output from these two AND gate to OR gate, since you have plus over here, plus, so we have this OR gate. Okay, so this looks somewhat like AND gate, you can just change. So the output would be x multiplied with y plus x multiplied with z. Okay, so you can verify that these two are same using a truth table as well. You can take x, y, z and you will find y plus z. After finding y plus z, you will multiply it with x, y plus z. Then you need to verify RHS as well, so we'll find x into y separately, then we'll find x multiplied with z, then we'll add these two. Okay, x plus y, sorry, x multiplied with y, it's x multiplied with y and x multiplied with z. Okay, so these are the columns that you would require in your truth table, and finally these two columns need to be same. So let's do this one. Okay, I'll verify this one for you guys. Okay, so these are the columns. So we have three input, right? So how many possible combination we'll have? It will be 2 raised to the power 3, which is 8. 2 raised to the power 3 is 8. 3 is the number of input. So let's find out all the possible combination. They are 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and finally 1 1 1. Okay, 1 2 3 4 5 6 7 8. Okay, so we have 8 combination. So I'll recommend that you follow this pattern. Why is, if you want you can shuffle them as well, no problem, but stick to one pattern. And why this possible combination? Because yeah, in number system I have taught you like how to evaluate these binary numbers. So this is 2 to the power 0 1 and 3. So this possible combination, that is 0 0 1, means 0 0 1. Okay, so I'll take one example. 1 is on, so therefore 2 to the power 0, which is nothing but 1. So if you'll take suppose this combination right over here, which is 1 0 0, so 1 is on, rest of these two are off, so you'll just neglect them. And sorry, it's 2 to the power 2. Okay, so 2 to the power 2 is 4. So this, if you want to represent 4, the equivalent binary number is 100. So you can see that this is arranged in 1 2 7. So let's find y plus z. Y plus z 0 1 1 1 0 1 1 1. Now let's multiply this with x. 0 0 0 0 0 1 1 1. Now let's find xy. 0 0 0 0 0 0 1 1. Let's find x multiplied with z, which is 0 0 0 0 0 1. This would be 0, this would be 1. Okay, so now add these two columns, which is 0 0 0 0 0 1 1 1. From here you can see that these two columns are same. Okay, so this first distributive law is verified using the truth table. So let's move on to the second distributive law. So the second distributive law is the dual of the first one. So the first one was x multiplied with y plus z is equal to x multiplied with y plus x multiplied with z. So now you'll apply POD, principle of duality. You'll get x plus y into z is equal to x plus y multiplied with x plus z. So this is your second distributive law. So this is the LHS and this one over here is the RHS. So let's draw the logic gate for these two. We have YZ. So YZ are being given to this AND gate. So you'll get y multiplied with z. Then we have x as well. Now you have plus over here, so you'll use a OR gate. Now the input are x and y into z. So the final output would be x plus y multiplied with z. Now we'll draw the logic gate for the RHS. we have x plus y, which means x and y are given to OR gate, and we have x plus z, so x and z are being given as input to a OR gate. As I told you, if you want you can even take a x from over here in the previous example as I've shown you, but I like to prefer this one because it's easy to draw and understand at the same time. Now these two are being multiplied, so this is x plus y, this is x plus z. Now they are being multiplied, which means we have AND gate over here. This is AND gate, and the final output would be x plus y and multiplied with x plus z. Okay, so now you can even verify this with the help of a truth table. So the column that you would require in the truth table would be x, y, z. Then you'll find y multiplied with z, then you'll add them. Now we'll do this for RHS. For like in RHS we have x plus y, then you'll find x plus z, and then you'll multiply these two. Okay, multiplied with x plus z. So these are the columns that you would need in your truth table. And finally these two columns, this one right over here should be same as the last column. Okay, so you can try that this by yourself. It's quite simple. Okay, so we have another third distributive law which states that x plus x complement y is equal to x plus y. Okay, so let's draw the the logic gate representation. So we have a x, we have x naught. If you want you can again pass this through a NOT gate, you'll get x complement, right? Whenever you pass x you'll get x complement as the output, and you have y over here. So now they are being multiplied, so you need a AND gate. So we have this AND gate, you'll get output as x complement multiplied with y. Now if you want you can take this x from here. Okay, now you need to pass them through OR gate. Okay, so your final output would be x plus x complement y. Now remember that you need to take x from over here, so which means you're taking x, but if you'll draw a line from over here and give it to this OR gate, which means that you're giving x complement. Okay, so it's really important that you know uh, draw the lines correctly, which if you draw from here it will mean that you're taking x complement, but if you'll draw the line or you'll take an input from over here, it means you're taking x. So just remember that. Now this is same as x plus y, so x plus y is really simple. You have x and y, you're passing them through OR gate, so you'll get x plus y. So this is not a AND gate, this is OR gate. Now again you can draw the truth table to verify this uh, third distributive law. So let's move on to our next Boolean law, which is the absorption law. Okay, so it states that x plus x into y is equal to x, and when you apply duality on this first one you'll get x multiplied with x plus y is equal to x. Okay, so let's verify this. Okay, so I'm leaving the third distributive law truth table as an exercise for you. Let's move on to our ninth Boolean law, which is the absorption, which state x plus x into y is equal to x. Okay, Now let's draw the gate representation. We have x multiplied with y, so this will be x multiplied with y, and you can, if you want, you can take another separate x, or you can draw one line from over here. It's your choice. So but I like to take another separate x. Okay, and we have this plus over here, so I'll draw a OR gate. Now our output would be x plus xy, which is same as x. Okay, so this is the gate representation, and let's verify this with help of a truth table. We have x, y, we'll find xy, then we'll add x plus xy. Okay, so since two input possible combination are 4, so 0 0 0 1 1 0 1 1. Now let's multiply these x and y. 0 0 0 1. Now let's add xy and x, so you'll get 0 0 1 1. So now you can see x and x plus y column, these two are same, so this distributive absorption law is verified. Now if you apply duality to this one, you'll get x multiplied with x plus y is equal to x. So let's draw the gate representation, x plus y. So we have OR gate with us, so you'll get x plus y. Now if you want, you can take another separate line from over here, but I like to take another separate x variable. So now we have this dot over here, so which means we have a AND gate, and the output will be x multiplied with x plus y, which is same as x. Okay, so let's again verify this with the help of truth table. X and y, x plus y, then we'll find x multiplied with x plus y. So possible combination of input are 0 0 0 1 1 0 1 1. Now let's find x plus y, which is 0 1 1 1. Now we'll multiply x plus y, this column, with x. 0 0 1 and multiplied with 1 1. So you can see again that the first and the last column are same, so this second absorption law or dual of the first one is verified. So in the next video I'll talk about De Morgan, which is our final Boolean law. But before ending this video, if you want, you can even prove this absorption law algebraically. Let's prove this first one. So x plus xy is equal to x, right? So in LHS we have x plus xy, but now if you'll take this x common, you'll get x 1 1 plus y, and x multiplied with 1, which is always equal to x. So 1 plus y, what is this? This is a property of 1. Under property of 1, you studied that whatever is whenever you add a variable with 1, you'll get 1, and whenever you multiplied 1 with any variable, you'll get the same variable, which is equal to x. Now this is same as your RHS. Now you can even do this for this dual one. The dual is x multiplied with x plus y. So this is our LHS. Now let's multiply this. Okay, x multiplied with x plus x multiplied with y. X multiplied with x is always x. This is idempotence law, plus x multiplied with y. Now again you can take x common out, you'll get 1 plus y. Now this part you'll solve this using property of 1, which is x into 1. Again you'll solve this by property of 1, which is x, and it is equal to our RHS. So now in the next we'll learn about De Morgan law, and that will be our final law. So I'll see you guys in my next video.